For decades, analysts believed this air corridor was predictable, but during one routine scan, something broke the pattern. A massive transport aircraft entered the zone at a speed that didn't add up, and every system started lighting up. What happened next pushed both nations into a moment no one was prepared for. Before we uncover why this maneuver defied expectations, stay with us. The truth unfolds one frame at a time.
Грай мяча.
The first readings show a massive aircraft entering Russian airspace at an unusually steady speed. Operators double-check their equipment, expecting sensor noise, but the signal remains solid. Early projections suggest the aircraft is holding a perfect line, almost too perfect. Analysts begin cross-referencing data, anticipating that any deviation could reveal its intent. As the aircraft continues forward, turbulence in the upper atmosphere starts shifting. The radar teams adjust filters to isolate real motion from environmental noise. Despite the unstable corridor, the aircraft maintains a velocity that pushes the limits for its size. The command center watches every fluctuation, searching for the first sign of abnormal behavior. The readings suddenly tighten, wind shear increases, yet the aircraft shows minimal correction. Operators note the anomaly and elevate the alert level. If the turbulence grows stronger, any miscalculation could force a shift in the aircraft's path. Ground crews prepare additional sensors to capture whatever comes next. Short bursts of instability start affecting the flight corridor. Data analysts see slight distortions around the aircraft signature, the kind typically caused by sudden pressure changes. The command center orders every console to run predictive models in real time. They need to know whether the aircraft will correct its course or break away from it. The trajectory begins to show its first meaningful deviation. Operators highlight the angle shift and compare it against known turbulence patterns. The divergence is small, but enough to trigger secondary monitoring. Teams across the base adjust their instruments, preparing for a wider deviation if the instability escalates. The aircraft's drift becomes more noticeable as winds shift across the upper corridor. Radar operators refine their readings, filtering out atmospheric static to isolate the true path. The deviation grows slowly, but steadily enough to raise concern. Analysts begin preparing alternate projections in case the aircraft breaks from its expected route. New turbulence hits the corridor, forcing the aircraft to adjust with sharper movements. Operators document each shift, noting patterns that don't align with normal compensation. The command center increases the alert threshold, anticipating that the aircraft may cross into a high-priority monitoring zone if the instability gets worse. Data feeds show a rhythm forming, sudden dips followed by quick recoveries. This oscillation is unusual for aircraft of that size, especially under crosswinds this strong. Technicians compare real-time measurements with historical models, searching for clues. The base prepares for escalating turbulence and possible loss of stable tracking. The drift now extends beyond earlier predictions. Wind pressure builds along the flight path and algorithms warn of potential deviations into restricted sectors. Operators brace for broader instability as the aircraft begins reacting more aggressively to every atmospheric shift. They prepare for the moment the turbulence overtakes the automatic controls. Trajectory models start showing larger gaps between predictions and the aircraft's real path. Instability is rising fast, and the command center orders all teams to expand their monitoring fields. This type of scenario is used in advanced training because it pushes every system to its limit. If you're following this analysis, stay close. The next decisions shape everything that comes next. Long-range antennas start picking up rapid shifts in the aircraft's heading. Prediction models struggle to keep pace, generating unstable trajectories that change every few seconds. Command orders all sensors to lock onto the critical corridor. Every variable now matters. Even the smallest fluctuation could signal a deeper loss of control. The Atlas 4A enters a pocket of unstable air where pressure changes hit hard and fast. Altitude drops begin appearing in short bursts. Analysts flag the readings and raise priority on atmospheric tracking. If the turbulence tightens any further, the aircraft could lose stable altitude long enough to trigger emergency assessments. The aircraft begins cycling through brief drops followed by sharp climbs. Systems interpret the pattern as forced autocorrection, push to the edge. Crosswinds intensify and teams shift to continuous monitoring. Each sudden movement tells the same story. The flight is nearing the upper limits of what its stabilization systems can handle. Data confirms that the aircraft is now fighting turbulence with unusually aggressive corrections. These maneuvers suggest the airflow is nearing critical strength. Command issues an internal alert, preparing for a possible intercept if the drift pushes into restricted zones. Every station tightens its focus. The Atlas 4A's path grows more unstable with every mile. Operators detect rapid swings in altitude and heading, each one stronger than the last. Command highlights multiple risk zones as potential breach points. Teams across the base coordinate to maintain steady eyes on the aircraft's oscillating signature. The aircraft closes in on the outer edge of a high-sensitivity sector. Updated models show the drift may enter restricted airspace if the instability persists. Technicians shift all resources to narrow-band readings, trying to determine whether the aircraft can recover its intended course before crossing the line. The oscillations intensify, forcing the command center to revise projections in real time. Wind shear grows sharper, shaking the aircraft's trajectory out of predictable patterns. Operators push for micro-variation tracking to capture every sudden move. The risk of temporary signal loss becomes increasingly likely. Short, rapid descents begin stacking into the data stream. The aircraft's motion shows heavy turbulence, the kind that can break tracking systems for seconds at a time. Command orders frame-by-frame analysis to keep the signal stable. The mission now depends on reading every shift the moment it happens. The aircraft starts performing movements that fall outside normal operating parameters. Rapid-fire variations overwhelm conventional tracking. Radar teams switch to high-speed data modes as command evaluates scenarios for a potential fighter verification. Conditions now meet the threshold for emergency visual contact. The sudden rightward turn causes the aircraft's echo to flicker across multiple screens. Sensor redundancy goes into full effect. Analysts run 2 predictive models at once, trying to rebuild the projected route. One more escalation in turbulence could make the echo vanish long enough to trigger a full alert. Signal drops begin appearing in quick flashes, a warning sign that the corridor's density is reaching extreme levels. Operators adjust parameters to track the disappearing echoes. Command drafts contingencies for temporary radar loss, knowing the next shift could push the aircraft beyond reliable detection.